In the next slide, we'll go through an experiment in which thin film aluminum was deposited on optical windows and allowed to naturally oxidize in air via step 1, physical vapor deposition or flash deposition of the thin film aluminum metal onto microscope glass substrates, followed by oxidation in air of thin film aluminum to aluminum oxide. Then we introduce the microscope glass samples into the DPAL gain cell emulator and then observe any changes in the deposited thin film aluminum layer. The next slide shows the physical vapor deposition of aluminum thin film, the point source model after McLeod, 2003. The next slide shows the physical vapor deposition of aluminum thin film via the point source model by McLeod. What you have is an omnidirectional expansion of the aluminum staple, the vapor, to deposit onto glass substrate on top in a bell jar. After heating the tungsten filament, the aluminum mass vaporizes and deposits onto the glass substrate. In the next slide, we show a MATLAB implementation for simulation of the point source model, which by varying the parameters, you can get the precise thickness of thin film aluminum deposited from a particular height, and so very useful code to manipulate the thickness of the thin film. In the next slide, we show an experiment in which from a certain height, the point source, 0.18 meters, a mass of 0.01 grams of aluminum would be required to deposit a thickness of aluminum film of 10 nanometers. In the actual experiment, we show at 0.18 meters approximately, an actual mass used based on physical limitations was 3 times what we initially wanted to do, which was 0.01, so it's 0.03, and so we have almost a scalable thickness theoretically, as shown in experiment 27.97 nanometer of aluminum deposited. In the next slide, using the Edwards high vacuum coating system, E306A, we perform this experiment, as you can see, in A, the equipment, in B, the inside of the bell jar, and C, making a measurement for the fixed height from the point source for aluminum, and in D, you could see the attachment of the aluminum staple onto the tungsten filament. The next slide shows the microscope slides before and after. You can see the circular target area on the microscope slides before, the circular target area on the microscope slides after, deposited with the aluminum thin film. And this was after the aluminum staple was heated by the tungsten filament and the flash deposition occurred. And in C, you can see essentially through a layer of aluminum oxide, which grows almost instantaneously, the excess of aluminum that was deposited, and it's there as a thin film beneath the aluminum oxide. So in the next slide, these 2 microscope slides were introduced to a DPAL gain cell emulator. And the DPAL gain cell emulator contains rubidium, methane to simulate the alkali laser environment. And the entire apparatus heated for a minimum of 14 days. And the results from that we'll take a look at in the next slide. In the next slide, we'll see the effects on the thin film witness sample after exposure to the rubidium vapor in the DPAL emulator. And as you can see, the top right is the sample after exposure to rubidium vapor in the DPAL emulator, and then on the bottom left, the unexposed or the reference sample. So in this case, the rubidium ate away at the protective layer of aluminum oxide and began to attack the thin film aluminum below it, and eventually essentially reacted away with the thin film aluminum to